Yeah, well, yeah, there's like one or something that flows this way.
All right. We are going to take a look at a few different aspects of graphs of equations here. All right, first, an ordered pair that satisfies an equation is called, now in the book they call it a solution, but I actually don't really like that term because we think of a solution as an x-intercept, right? So they're saying a solution to an equation is any point on the graph, which I don't really like that terminology, okay? But that's what the book says. So graphically, this means a point on the graph. So in an ordered pair, x, y, x is the dependent variable, and y is the, nope, that's wrong. X is the independent variable, and y is the dependent variable. There we go. X is the independent variable, y is the dependent variable. Okay, so first, we just want to think about are certain points on a graph, right? How would I test that? How would I test if the point 1, 0 is on the graph, x squared minus y squared equals 1? Plug it in, see if it's true. Right? So I'm going to plug in 1 for x, 0 for y, and see if I get a true statement. So 1 squared minus 0 squared, does that equal 1? Yes, right? 1 minus 0 is 1. That is true. So, yes, the point 1, 0 is on this graph. Take a minute and try the next three. Okay, see if those 3 coordinate points are on x squared minus y squared equals 1. You guys don't have to be silent here. You can talk with each other.
That would be the funnest thing ever. I mean, I didn't agree with any. What's that do? Don't send me back. Dude, you can't just go to our phone.
All right, did we get yes, no, yes, yes? Okay. Feel okay with checking to see if a point is on a graph? All right. So we're going to skip this discuss part here, all right, and talk about finding intercepts, right? Finding intercepts is one of the more important things that we can do with an equation, right? It has lots of different applications, right? And that's what we practice doing a lot, right? Finding solutions, right, is finding intercepts of an equation. So to find a y-intercept, what do we do? Stuff. To find a y-intercept, we let what? What do we do? What happens? How do we find a y-intercept?
I don't know how the words would fit into the guided notes.
That's it. To find a y-intercept, we let x equal 0 and solve for y. Because you got a question, right? I don't think that's how this works.
You maybe need the italic thinking you're getting the right answer.
How do we find an x-intercept? We let y equal 0 and solve for x. Right, hopefully, graphically, that makes sense, right? If we're thinking in terms of a graph, if I want to find where a graph crosses the y-axis, right, a y-intercept, well, that's going to be where x is 0. Similarly, if I want to find where we have an x-intercept, that's going to be where y equals 0. Okay, so in these examples here, okay, to solve for x and y-intercepts, so first, if I want to find a y-intercept, I'm going to let x equal 0, solve for y. Right? So plug 0 in here for x, so I would have 0 over 2 minus y over 3 equals 1. 0 over 2 is just 0. Right? So I've got negative y over 3 equals 1. What do? Multiply by 3. Yeah, so to save us a step, we could multiply both sides by negative 3, and then we will have y by itself. Right, and we get y equals negative 3 for the y-intercept. So what would that coordinate point be then? If I wanted to write that as a coordinate point with an x and a y. 0, negative 3. Right? We just said our x is 0 here, so the y-intercept would be 0, negative 3. So for the x-intercept, we're just going to plug 0 in for y. So I will have x over 2 minus 0 over 3. So this one, we don't have to deal with any negative signs, right? Just multiply both sides by 2, and we get x equals 2. So what would that coordinate point be then? 0. Try the second one here. Find me the x and the y intercepts for b. And. You should have 2 answers for each one. 2 x-intercepts and 2 y-intercepts. Be intimidating.
Trying. Does that mean we get 4 answers? Stop. There's going to be a lot of it. Are you going to write it myself?
we get 4 intercepts here?
Yeah.
2y and 2x. Yeah. So 0, 5, and 0, -5 for the y-intercepts. 5, 0, and -5, 0 for the x-intercepts. What does the graph of this look like? What does x squared plus y squared equals 25? It's one of those things. Well, let's think about.
It's the one that goes like that.
It does do something like this. Let's think about the 4 points that we just found. Right? I found 0, 5, and 0, -5. And 5, 0, and -5, 0. This is going to be a circle.
That's a circle?
It's a circle.
Man, that's pretty cool.
Right?
I've never seen one of those. Because in a circle goes x and y are squared the equation.
Right. Also in an ellipse, but you'll have different values underneath of the x and the y. Alright, we're actually part of this lesson. The last part is about equations of circles. I don't know why that's part of this lesson, but we're going to talk about equations of circles here in a minute. Do we feel comfortable with finding x and y intercepts? Okay. To find an x-intercept, plug 0 in for y. To find a y-intercept, plug 0 in for x. Alright. So, next is graphing. Okay? Maybe not the easiest way, but a foolproof way of graphing an equation is to make a table. Right? That will always work. Right? It might be a little tedious. It might take a little bit more time than if you understood what the graph looked like in the first place. But this would always work to make a graph of an equation. Okay, so we're going to practice that. Okay, we're going to sketch out the graph of x squared plus 2x minus 8 using a table. So I need to fill in the y values. How do I do that?
Plug in the x and x values.
Plug in the x values. What's up?
On the calculator, we make a specific number set for x. So you can type x.
Store. So that STO button down at the bottom. So if you want to. Alright, so go ahead and do this here real quick. Fill in this table. Get me these y values.
What if I don't want it?
I don't care. Do it anyway.
It was a joke, I'm sorry. Say what? I don't know. So, Mr. Fetch is the most adamant child.
What?
So you just hate children.
Is their name Jax?
Hey, that's
I'm kidding.
enough. So you're not. No. Mr. Fetch is like, I have really strong PTSD.
Now that's one I'll sign.
Let's go.
That was a high five. Oh man, how does this taste? It's so weird.
Did we get something like this?
Yeah, I thought we were.
No. This is a parabola.
Weirdest circle I've ever seen.
I'm not grabbing that.
All right, any questions on using a table to sketch a graph? All right, then next, let's talk about symmetry. Okay, we can talk about symmetry across the x, the y, or the origin. All right, so graphically, okay, if we're talking about symmetry across the x-axis, okay, we want to be able to fold something across the x-axis and it matches up, right? So an example of symmetry across the x-axis might look something like that. Right? That could be an example of something with symmetry across the x-axis. What might something with symmetry across the y-axis look like? A parabola, sure. We could say that has symmetry across the y-axis. Right? If we just fold something across the y-axis, it lines up. What does symmetry across the origin mean? This one's a little tougher to visualize. I think these two are pretty easy to visualize, right? If we just fold across one of the axes, it lines up exactly. But what might symmetry across or about the origin mean? Yeah, right? The easiest example is usually the cubic function. Right? This is an example of symmetry about the origin. Okay? It's tougher to visualize because you can't really just think about folding. Right? It's symmetry through the origin. Right? This one I think actually makes a little bit more sense when we talk about it algebraically. The x-axis and y-axis hopefully make a lot of sense just looking at it graphically. Okay? But symmetry across the origin isn't as intuitive just looking at a graph. All right? So algebraically, what this means, okay, if we have a point xy on a graph, then the point, and I always mess these up, so I got to make sure I write this down correctly. Then the point, negative x, y will also be on the graph. Nope, that's wrong. I just think that doesn't sound right. X negative y. Yeah, that makes more sense. So, in terms of a graph, right, if we're saying that this is the point xy right here, okay, in order for this to have symmetry across the x-axis, this point down here would have to be x negative y. Okay, the exact same x coordinate, but the opposite y coordinate. Similar idea for the y-axis. Right? We would have to have negative x, y on that graph. So here, if I've got the point x, y on the graph, then over here would have to be the point negative x, y. Right? The same y coordinate, opposite x coordinate. In order for us to have symmetry with respect to the origin, I have to have the opposite set of both coordinates. Negative x, negative y. So on this graph, if I have xy, that means down here I have the point negative x, negative y. Right, so to put some numbers to that, right, if I've got the point 2, 1 on this graph, that means the point 2, negative 1 is also there. If I've got the point 2, 1 on this graph, that means the point negative 2, 1 is here. And if I've got the point 2, 1 on this graph, negative 2, negative 1 is also on that graph. All right? We okay with that? So let's look at what it would mean to actually test this, okay, in an actual example. And if I want to test for all three types of symmetry, okay, from this equation here, 2x cubed minus x, what we're going to do, okay, if I'm testing for symmetry across the x-axis, right, this was the one we said if we have the point xy on the graph, I always have to think about it. So if I'm flipping across the x-axis, that's going to be the same x-coordinate, opposite y-coordinate, right? Well, what I'm going to do then is take this equation and substitute negative y in place of the y that I already see, okay? So I'm going to say negative y equals 2x cubed minus x. And now, I want to solve for y again. Okay, well, to solve for y, I'm just going to divide both sides by negative 1. So I have y equals negative 2x cubed plus x. Now, what we want to look for is if we end up with the same equation that we started with. Do I end up with the same equation that I started with? No, right? That means that this does not have symmetry across the x-axis. To test for symmetry across the y-axis, right, that's the one where we're saying, well, if xy is on the graph, then negative x, y is on the graph. So in this case, I want to plug in negative x into my equation everywhere I see an x. So I'm going to say y equals 2 times negative x cubed minus negative x. And simplify, right? So what's negative x cubed? Negative x cubed, right? If I've got negative x times negative x times negative x, I will have a negative x cubed. So this would end up being negative 2x cubed minus negative x. So plus x, right? Do I end up with the same thing that I started with?
No.
No. So this does not have symmetry across the y-axis either. Now, let's test for symmetry about the origin. Okay? This is the one where we said, well, if we've got xy on the graph, then negative x, negative y is on them. So I'm going to replace both x and y with negative x and negative y. So negative y equals 2 times negative x cubed minus negative x. Okay. So I get negative y equals, and this is the same simplification as the last one, right? So negative 2x cubed plus x. Divide both sides by negative 1 to get y by itself. And we end up with y equals 2x cubed minus x. Is that what we started with? Yes. So this graph does have symmetry about the origin. Not across the x or the y-axis, but it does have symmetry across the origin. Okay. We okay with that?